wabarakatuh. In this video, I will teach you the next method in analysis of heat exchanger. The name of this method is Effectiveness-NTU method. So first, we already learned about the log mean temperature difference. An overview of this method has been explained in the previous video. So in this video, I will explain on the Effectiveness-NTU method. So this method is based on dimensionless parameter. So the dimensionless parameter is epsilon here. As we can see here, this epsilon represents the dimensionless parameter, or we call it as heat transfer effectiveness. So how to calculate the heat transfer effectiveness? Here we have equation of actual heat transfer rate divided by maximum possible heat transfer rate. This is equation for you to find what is the effectiveness, so epsilon. Okay, for you to calculate what is the actual heat transfer rate is by using equation. As you know that the equation for you to find what is the rate of heat transfer on the cold side and hot side will be determined by this equation. So C, capital letter C, is represent heat capacity. So this equation is actually from M dot C times with CPC. So this equation is equal to heat capacity. So you have to times with TC out minus TC in. This is the cold side. Okay. For the hot side, we have CH, specific heat capacity, hot side, and then TH in minus TH out. I already explained why does this equation rearrange like this. Normally we know that to find what is the delta T, the gradient, temperature gradient, we have to minus the exit with the inlet. But here we have a different arrangement of this equation. This is because TH in is much more greater than TH out. That's why the arrangement is a bit different here. This equation will give you a positive value. And it doesn't matter if you are using these kinds of equation, or maybe you want to change this equation into TH out minus TH in to fulfill the delta T requirements, where we have to minus exit temperature with inlet temperature. You can use TH out minus TH in, but in this equation you will get the negative value. Okay, that negative value represents a release of energy. So in order for you to substitute that Q dot values to other equation, you must not bring negative values together with that value. Okay, you must take only a positive value. So now the maximum temperature difference, from here we have to calculate what is the maximum possible heat transfer rate. So the maximum possible heat transfer rate comes from the maximum temperature gradients that system can achieve. Okay, why this equation becomes TH in minus TC in? So as we can refer or try to figure figure the double pipe heat exchanger, for example. I draw it. Okay, very simple one. So we have a double pipe heat exchanger where in the middle of this pipe we have tubes. Okay, smaller pipe into a larger pipe. So we have two different pipes here. So now we have TC in and we have TC out, and TH in, TH out. So now we want to calculate what is the delta T maximum. What is the maximum temperature gradient for this system can achieve. Okay, to determine what is the delta T maximum, so we have to take a look at the inlet temperature. We know that the inlet temperature is TH in. Okay, that is the highest temperature in this system, right? The highest temperature. We have to take a look at the highest temperature, and the other one is lowest temperature. Okay, this will come out with delta T maximum. So you have to take a look at TH in, TC out, TH out, and TC in. So from these four temperature, which one has the highest temperature? Of course, TH in has the highest temperature. Okay. Next, we have to take a look at the lowest temperature. Is it TC out or TH out? No, TC in. So this temperature can bring down up to this temperature. So the lowest temperature in this system is TC in. So we have to minus TC in. Therefore, we will get what is the delta T maximum for this system. Okay. So to find what is the delta T maximum, you have to find what is the maximum temperature or the highest temperature between TH out, TC out, TH out, and TC in. Okay, and then minus with the lowest temperature. So the lowest temperature here is TC in. So TH in minus TC in will give you maximum temperature difference. This maximum temperature difference also means that when you have, for example, you have your hot fluid from 80 degrees Celsius, for example, and then your TC in is 20 degrees Celsius. Your system can further reduce this temperature up to 20 degrees Celsius only, and it will not reduce further, or it will not reduce below than 20 degrees Celsius. Okay, so 80 degrees Celsius can can drop up to maximum to 20 degrees Celsius. Okay, it will not drop. For example, will not drop to 80 degrees Celsius or 17 degrees Celsius because the lowest temperature in this system is 20 degrees Celsius. Therefore, 80 degrees Celsius can only be reduced up to 20 degrees, 80 degrees Celsius can further reduce until 20 degrees Celsius. Okay, so that's why if you are subtracting TH out and TH in, the hot inside into the system with the TC in, T cold into the system, you will get what is the maximum temperature gradient for your hot fluid can achieve, or for your system can achieve, or for your cool fluid can achieve. Okay, maybe your temperature here 20 degree up to 80 degree. It can further increase up to 80 degrees Celsius. For TH in, it will reduce further to 20 degrees Celsius. That is the maximum. Maximum temperature or the highest temperature minus with the lowest temperature, you will get the delta T, temperature gradient, maximum temperature gradient for that system. Okay, so that is maximum temperature difference. Why do we need to calculate delta T max? Because we want to calculate what is the maximum possible heat transfer rate. So the maximum possible heat transfer rate in the heat exchanger is Q dot maximum equal to C minimum delta T max equal to C minimum TH in minus TC in. Okay, for this, I have to explain a little bit more. Okay, I use a white screen. So in this equation, okay, Q dot equal to CC D C out minus D C in. This is the first equation. And the second equation is Q dot for hot. And this is Q dot for cold. So CH D, so TH in minus TH out. So we have these two equations. Now in the question, in order for you to determine Q maximum, you have to use C minimum. And TH in minus TC in. What is this value? C minimum. So from here, we have cold fluid, specific heat capacity for cold fluid and specific heat capacity for hot fluid. So where do we get the minimum heat capacity? Okay, here this is delta T maximum. Okay, but why does this have a minimum? Why do we choose minimum specific heat capacity? Why don't we also choose maximum specific heat capacity? Because we want to calculate what is the maximum. Okay, let me give you some illustration. For example, you have water. Okay, you want to bring your water from well and you want to pour it into a bottle. So you bring this water from the well, okay, about 2 liter, okay, 2 liter of water from well, okay, and then you want to transfer it into a bottle, okay, with a capacity of 1.5 liter, okay. Can you refill or fill up this bottle, okay, bottle, which capacity is up to 1.5 liter with 2 liter of water? Can you fill up? No. Of course, no. Because your maximum, the maximum water that can be transferred is only 1.5 liter. Okay? So that is the maximum value. That is the maximum amount of water that can be transferred and that can be stored by you in the bottle. Now, imagine that you have C, for example, and then CH here. So you calculate both of these specific heat capacity. So if your specific heat capacity for hot is 1.5, whereas CC heat capacity for cold fluid is 2. So the maximum for the system, this is Q dot max, the maximum that this system can transfer or release or absorb is only 1.5 liter or 1.5. Here we know that CH is a minimum. Therefore, this is C minimum. In order for you to calculate what is the rate of heat transfer, maximum rate of heat transfer, you have to use C minimum. Even you have CC with the largest value, with the large values of heat capacity, you still have to choose minimum heat capacity because that is the amount of energy that can be transferred or absorbed by the system. And that amount, if you transfer 1.5 liter here water, then you can fill up this bottle. If you transfer 2 liter, about 0.5 liter will flows out. So the maximum that this can receive or store water can be stored is 1.5 liter. And if we can see here, this amount of this bottle capacity is the minimum capacity for this condition. Therefore, in order for you to know what is the maximum water that can be filled up into the bottle, you have to use, or the maximum water that can be filled up in this bottle and transferred back to the well is about 1.5 liter. So if you go and take 1.5 liter, I change the color. I take blue. So from the well, you take 1.5 liter. Yes, your amount of energy here is amount of water that can be filled up is 1.5 liter. So you can transfer to this water, to this bottle, and then from bottle can transfer back to the well. Or maybe you want to take out 2 liter. If you are take out 2 liter from the well, you can only transfer 1.5 liter to the bottle. And then from the bottle can only transfer 1.5 liter. So that is the maximum. That's why here we have to compare CC and CH and find the lowest C. Okay, lowest heat capacity, then the lowest will be C minimum. Okay, compare between CC and CH, find the lowest C and then take out that C as C minimum. Okay, and C minimum times with delta T maximum, you will get what is the value of Q dot maximum. Okay. Next, once the effectiveness of the heat exchanger is known, the actual heat transfer rate can be determined from Q dot equal to epsilon Q dot maximum. This equation is actually comes from previous equation here. So we have the effectiveness Q dot over Q dot maximum. So Q dot over Q dot maximum. Okay. So if you have effectiveness value here, sometimes if the question give you the effectiveness, then you have to calculate what is the actual. So this is actual. What is the actual rate of heat transfer or actual heat transfer rate? You just rearrange this equation, yeah? Q dot equal to epsilon times with Q dot maximum. So you will get what is the Q dot. Okay? And from here, we know that Q dot maximum is C minimum times with TH in minus TC E. So this effectiveness is depends on two condition, where two parameters of condition. One is the geometry of heat exchanger, and second is flow arrangement. So it can be shown that the effectiveness of double pipe parallel flow heat exchanger is, so this is the equation, epsilon parallel flow. Okay, so 1 minus exponential minus UAS over C minimum, 1 plus C minimum over C max over 1 plus C min over C maximum. So you don't have to worry because all these equation will be provided in the exam. So effectiveness relation of the heat exchanger typically involve a dimensionless group called the number of transfer unit. So NTU is UAS over C minimum. So U is overall heat transfer coefficient. So overall heat transfer coefficient. Okay. AS is heat transfer area, surface heat transfer area, and C minimum is minimum heat capacity. So here, C minimum, we know that in order for you to calculate what is the heat capacity, you have to multiply m dot with specific heat capacity. Okay, so you will get C minimum. So this is the equation for NTU. For specified values of U and C minimum, the value of NTU is measured of the heat transfer surface area ES. And then the larger the NTU, the larger the heat exchanger. So NTU value, so larger NTU, larger heat exchanger. So it is convenient to define a capacity ratio. So this capacity ratio C equal to C minimum over C maximum. Okay, this is the equation. You have to remember this and this. But you don't have to worry because in the chart or in the table, all of these equation will be given, okay, provided in that table. The effectiveness of the heat exchanger is a function of the number of transfer unit NTU and the capacity ratio. So for you to calculate what is the effectiveness, you have to know the value of NTU and capacity ratio. So this is you don't have to worry because all these values, if you calculate NTU or C, then you will refer to this table. So we have two types of table. So one is table 11.4, where you know what is the value of NTU, which means that from here, you can calculate what is the value of NTU. So this table can be used if you know the value of NTU. So you substitute the value of overall heat transfer coefficient, surface area over C minimum, then you will get what is the value of NTU method, and C equal to C minimum over C maximum. So you can calculate both of these values, so NTU and C. Then you can refer to this figure or table. So from this table, we know that this is the heat exchanger type. So you have double pipe. Take a look. You have to read through the question, and then after that you determine what is the exchanger type. So one is double pipe, parallel flow. Double pipe. So for you to know or to calculate what is the effectiveness, therefore you have to define under double pipe, is it parallel or counter flow? If counter flow, then you can take out this equation. Okay, take out this equation and substitute all the values inside. Okay, then you will get what is the effectiveness, and after that you can calculate what is the actual heat transfer rate by using the effectiveness equation. Epsilon equal to Q dot over Q dot maximum. Or you can calculate the required or the aim, the objective, whatever objectives from the equation. Okay, that is number one. So we have another table. Okay, sorry. This is number one, is example 11.4. We have another table graph, and I will explain more on that graph after this, after next video, where in that video is specifically focus more on all the graphs that will be used in the chapter 4. So for now, you will be introduced with only table 11.4. We are actually have two types of two tables, 11.4 and 11.5. 11.5 for you know the value of effectiveness, then you want to calculate what is the NTU. Okay, so 11, sorry. Okay, for 11.4, so you know known NTU. For 11.5, known effectiveness. Known NTU, we want to find what is the value of effectiveness. If you know the value of effectiveness, you want to calculate what is NTU. Normally, the equation that provided you with effectiveness will ask you about the area length of the heat exchanger, because from effectiveness you can get the NTU. Then from NTU you can get what is the surface area. From the surface area they might ask you about the diameter or maybe the length of the heat exchanger. Okay, so this is effectiveness heat exchanger plot. So you are not only can refer your value of effectiveness from the figure from the tables. So this is table. We have two tables, 11.4 and 11.5. From that table values, there are transferring or plotting the values into the chart here. So you are actually can refer to this chart in order for you to determine what is the effectiveness. So from here, you can see here, you have to calculate what is the NTU and then see here. So if you already get what is the NTU, for example 2, and then you have to drag and draw a straight line up to 100 and then check on your C minimum over C maximum. Let's say you have a 0.75 here. Okay, so drag and take a look at what is the effectiveness. Point of intersection, you have to calculate what is the point, or you have to take and draw a line at a point of intersection. Okay, so if you have the values in between, so you have to interpolate and find the point of intersection. Okay, so again you have to take a look at this name of this chart. So A is parallel flow, B is counter flow, C is 1 shell pass and 2, 4, 6 tube passes, D is 2 shell passes and 4, 8, 12 tube passes, and then this 2 is for cross flow. Okay, mix and unmixed. So you have to take a look at this name of the chart. Okay, select a proper chart or select a suitable chart in order for you to determine what is the effectiveness. This chart is only to determine what is the effectiveness of your heat exchanger. It will never, or it can't determine your NTU values. Okay, so if you are not know, or there is no information gives to you in the question that that you can calculate the NTU values, therefore you have to use the tables. Okay, 11.5. Okay, for sure, if the question wants you to find what is the NTU, it will provide you with effectiveness. Okay, so the selection of heat exchanger, that is all about the effectiveness NTU method. I believe that maybe you have a little bit confusing about the terms and the concept and the way how we calculate the effectiveness NTU method. You don't have to worry. You have to refer to the example to escalate your understanding and to make you much more understanding about the LMTD method and NTU, effectiveness NTU methods. I believe that from that example, you will understand more about both of these methods. Okay, now we go to the selection of heat exchanger. An engineer going through catalogs of heat exchanger manufacturers will be overwhelmed by the type and number of readily available off-the-shelf heat exchanger. So the proper selection depends on the several factors. So heat transfer rate. So which of these types of heat exchanger will give you a proper or best heat transfer rate. Okay, then if you choose, for example, shell and tube, what about the cost? Or you want to select compact heat exchanger, you have to understand the cost of the fabrication. So not only fabrication, when you buy that equipment or you buy that heat exchanger, you have to understand all those factors, such as like procurement, maintenance, and power. Okay, then if you buy heat exchanger or buy heat exchanger, and you have to understand about the pumping power, because you have to understand what kinds of fluid that will be pumped into the uh, heat exchanger. The pumping power is equivalent to the pump size. If you requires a bigger pumping power, therefore you will have a big pump. And to have a big pump, it will again will affect to the cost of the manufacturing or fabricating. And size and weight. If for example you take a look at your cars or your father cars, your parent cars, radiator is being fabricated for the uh, small area. Okay, and if you want to do some heat transfer process in your factory or in a factory, it is better for you to choose shell and uh, tube heat exchanger. Do not choose a compact heat exchanger, because it is not suitable, and it must depends on other factors, for example types, materials, and then miscellaneous, for example leak type, safety and reliability, and quietness. That is all the factors, factors in order for you to select for the heat exchanger. Okay, thank you.